2007 Grade 10 Galois Math Contest. Jim shops at a strange fruit store. Instead of putting prices on each item, the math store owner will answer questions about combinations of items. In aisle 1, Jim receives the following answers to his question. What is the sum of the prices of an apple and a cherry? What is the sum of the prices of a banana and a cherry? What is the difference between the prices, and which is the higher price? Okay, so according to this information, apple plus a cherry is equal to 62. And similarly, a banana plus a cherry is equal to 66. So all you really have to do is just subtract those equations. So on this side it'll be 4, the c's disappear, and then it'll be b minus a. So b minus a is 4, and that basically represents the difference. That's the answer to the first part of the question. And then which is higher? Well, obviously b has to be greater than a in order for the difference to be a positive number. So that answers the second question. Part B. In aisle 2, Jim receives the following answers. What is the price of a pear? So very similarly, mango plus a nectarine is 60. And then pear plus a nectarine is also 60. And mango plus a pear is 68. So I guess from these two equations, we can conclude that m is the same as p, right? If you subtract them, you would get m minus p is 0, right? If you subtracted those two equations, and then that would lead to m equals p. And then what we can do is substitute that into here. So m plus m is 68, or p plus p is 68, whichever way you want to do it. And this gives 2p is 68, and therefore p would be equal to 34. So that's the price of a pear. And part C, Jim receives the following answers. What is the price of 11? So again, same story. T plus L is 60 this time. Tangerine plus grapefruit. Actually, no, this statement is a little bit different. How much more does a tangerine cost than a grapefruit? So G plus 6 is equal to T. That's sort of the interpretation of that sentence. And then the last one, the sum of the prices of all three. So G plus T plus L is 94. Okay, so this is the system of equations we have to solve. So off we go. Well, we can substitute that in there. So G plus 60 is 94. So that immediately allows us to solve for G, which would be 34. And then we can use use this one, I should say, to get T. So T is going to be 34 plus 6, and therefore T is 40. And then finally, to get L, I guess we can use this one. So T plus L, well, T is 40 plus L is 60. So therefore L is 20. And there you go. In the diagram, what is the perimeter of the sector of the circle with radius 12? Explain how you obtained your answer. Okay, well, these kinds of questions, what you do is you use the pi r squared formula, but it's not a full circle, right? It's a sector. So what fraction of the full circle? That's where you look at the angle. The full circle is 360 degrees, but in this case, we only have 60 degrees of it. So you would multiply pi r squared by that fraction. And that's pretty much it for area. And that's going to lead into the other parts. But then this question is asking about perimeter. So perimeter is a little bit different. They told me that the radius is 12. So OA and OB are 12. And then we have to figure out the length of that arc. So arc AB, that's a segment of the circumference. Now, how much of it? Well, same kind of story. 60 over 360. That much of the circumference. Now, circumference of a circle, I'll write it over here, is equal to pi times diameter. It can also be written as pi times 2 times the radius. So that's what I'll put in here. Pi times 2 times the radius, which is 12. And that pretty much is how you'd figure this out. So this is going to be, let's see here, I think 4 pi. Yeah. So that arc is 4 pi. So therefore the perimeter, P, is 12 plus 12 plus 4 pi, which is 24 plus 4 pi. And that solves part A. Part B, now we have two sectors of a circle of radius 12 that are placed side by side as shown. Determine the area of the figure. Okay, so this is where this formula comes in. And we have two of them. So it'd be 2 multiplied by that formula. So it's pi r squared, pi r is still 12, right? Yeah, 12 squared. And then each of those is the fraction 60 over 360. So that's basically the formula. So this looks to me like 2 times pi times 144 times 1 over 6. And that would be what? 144 divided by 3, which I think is 48. So 48 pi. Part C. In the diagram, AOB is a sector of a circle with angle AOB is 60. OY is drawn perpendicular to AB and it intersects AB at X. What is the length of XY? Okay, so let's see here. If this is 60 AOB, that means each of these guys is going to be 30. And therefore, since this is a right angle, and that's 30, this is going to be 60. So we have a 60, 30, 90 triangle. So I'll just draw it over here to make it a little bit cleaner. So we have 30 degrees and 60 degrees, and this is 12. Now the ratio of the sides of any 30, 60, 90 triangle, as I'm sure you know by now, is 2, 1, and root 3. That's the ratio. So if this is 12, then that means this is 6, and this is 6 root 3. This side. Okay, great. So what are they asking for? XY. Well, XY, if you look over here at this diagram, is really OY minus OX, correct? So OY, well, that's just the radius, so that's 12. And then OX, we figured out, this is O, this is X, so that's 6 root 3. And that's it. That's the answer to C. And finally, part D. Two sectors of a circle of radius 12 overlap as shown. Determine the area of the shaded region. Explain how you got your answer. Okay, so this shaded region has been chopped into half, right? So area of the shaded region, AS, is going to be 2 times each of these. And each of these I will call A, like that. You see how that shaded region is cut in half, and I'll just call one part A. Now, so 2 times A, I guess. So let's just concentrate on figuring out A first, and then we'll multiply it by 2. So A looks to me like it's the sector PQS, right? That sector, I'll sort of draw it here where it's got that curve. That's the sector. And then from it, you subtract the triangle PQS, which is basically the straight down. And if you do that, then you'll get that shaded region A. It'd actually be this one, the one that's on the right side. But they're both the same, so it doesn't really matter. Okay, so let's concentrate on this. So sector PQS, and we've done this in the previous part, so it should be no problem. Remember, it's that pi r squared and then 60 over 360, where r is 12 again. And then the triangle, well, that's 1/2 base times height. And the base, I think we have to look at the previous one because it's the same story, right? The base is going to be QS. And the height, I guess if we were to draw a line straight from P all the way to there, like that. And that would be, well, whatever we want to call it, but we've already calculated that OX. It's this one right here. So that's 6 root 3. Yeah, so it's pretty much the same as the previous question, and QS is like AB over here. Well, that would be 12 because that's 6. So you just have to double that. So it would be 12. So this is going to be 12. All right. So I think I have pretty much everything that I need. So pi, well, the radius is 12. And this is 1 over 6. And then we have 1/2. 12 times 6 root 3. Okay, so let's crunch out these numbers. This looks to me like 144 over 6, which I believe is 24. So 24 pi, and this is 6 times 6, so 36 root 3. But remember, area of the shaded region is 2 times that AS. So area of the shaded region is 2A, which basically would mean it's 48 pi minus 72 root 3. Number 3, each face of a 5 by 5 by 5 wooden cube is divided into 1 by 1 squares. Each square is painted black or white, as shown. Next, the cube is cut into 1 by 1 by 1 cubes. How many of these cubes have at least 2 painted faces? Explain how you obtained your answer. All right, this question was a little confusing because they wanted painted faces, right? So when I first looked at this diagram, I thought, okay, the only painted faces are the ones that I see in black. So these guys, these guys, these guys. But they are calling white paint as paint. You understand what I'm saying? So even the ones that are white are considered painted. And that's super confusing. I wish they had used a different color, like black and gray or whatever, right? Black and blue or black and red. But anyhow, I don't know if I'm the only person in the world who got confused by that. But anyways, here we go. So let's go through this problem. And let's talk about it. So I'm going to look at it from the level of layers. So let me explain what I mean. So in a cube, you got this first layer, right? The one that's closest to you, that layer. And then this is my second layer. And then third layer. However you want to do it, really. It doesn't really matter. So I've got layer 1, layer 2, layer 3, layer 4, layer 5, right? Okay. So at least 2 painted faces. That means I've got to count, basically. So I do. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So basically, any of the cubes that are in the perimeter will have at least 2 painted faces. And remember, paint is counted as white paint or black paint. The corners, of course, have 3 painted faces. And these middle guys, like this one, for example, this one, they have 2 painted faces. So when I counted, I got 16. And in a very similar way, the last layer is identical to the first layer. It behaves in the same way. So if 16 for the first one, 16 for the fifth one. Now let's go to the second one, this one right here. The only ones here that will have 2 painted faces are the corners. That one, and then this corner and that corner. These middle guys will have only 1 painted face. So since there's 4 corners, there's 4 there. And similarly, in this particular cube, the fourth layer behaves like the second layer. So that's 4. And then if you look at the third layer, this one, same story. The corners will be painted 2 sides, and the rest will have only 1 side. So there's 4 there. So if you add all these up, you get 44. And like I said, whatever system you want to use is fine, as long as you come to the right answer. Okay, let's keep the diagram in there. Part B this time, a 2k plus 1 by 2k plus 1 by 2k plus 1 cube, where k is a positive integer, is painted in the same manner as the 5 by 5 by 5 cube, with white squares in the corners. Again, the cube is cut into 1 by 1 by 1 cubes. In terms of k, how many of these cubes have exactly 2 white faces? Okay. Well, let's see here. Exactly 2 white faces. So instead of trying to draw this, I'm just going to look at this one here. Just look at the edges, because you want, what are they saying? Exactly 2. So this is a little bit different. Exactly 2 would mean that you would need something like this. You see these guys? Let me use a different color. It might be a little bit more obvious. This one, that's exactly 2. These guys are exactly 2. And although you can't see the other side, that one, this one, and this one will have exactly 2. So my advice is to look at those edges. And we have 12 edges, right? We have 1, 2, 3, 4. And then you'd have 4 on the other side. And then you have 1, 2, 3, and 4. So 4, 4, and 4, there'd be 12 edges. So 12 of them. And then each edge has, in this case, here. But we got to be careful here, because again, we got to concentrate on the color. They're saying white. So actually, we're really looking at that guy. Let me draw a different color here. We're looking at this guy here. So it's this one. So in our example up here, we've only got 1 per edge. Yeah. Because it's specifically exactly 2 white faces. So in this case, I guess it'd be 12 times 1. But they are not asking for this cube. They're asking for this cube here. So when you look at it from the perspective of the 2k plus 1, the number of edges stays the same. But each edge would therefore have k minus 1. Because when 2k plus 1 is equal to 5, which is this example, that means k is equal to 2. So if k is equal to 2 and this is 1, that means it's k minus 1. So very similarly, you'd multiply 12 times k minus 1, and that becomes 12k minus 12. And that is basically the answer to this in terms of k. And then part 2, prove that there is no value of k for which the number of cubes have at least 2 white faces. Okay, so basically what that means is they're saying that this 12k minus 12, we have to incorporate that, but this time at least 2. Okay, so at least two white faces means 2 white faces or 3 white faces. Well, 2 white faces is this guy, exactly 2 white faces, and then we got 12k minus 12 for that. 3 white faces are these corners right here. Let me show you. This is a corner right here. That's a corner. And every cube has 8 corners, right? So you'd have to add these. So it'd be 12k minus 12 plus 8. And that's 12k minus 4. So 12k minus 4 is how many, is the number for at least 2 white faces. Now they're saying that we want that to equal 2006. Okay, so 12k minus 4 is equal to 2006. That means 12k is equal to 2010. So that would mean k is equal to, if you divide through, 167.5. Now, that's not possible because k has to be an integer, right? They even tell you that. So therefore, you can write out in a sentence that because k is not an integer, there is no value of k for which the number of cubes having at least 2 white faces is 2006. Number 4. Jill has a container of small cylindrical rods in 6 different colors. Each color of rod has a different length as summarized in the chart. These rods can be attached together to form a pole. There are 2 ways to choose a set of yellow and green rods that will form a pole 29 centimeters in length. either 8 green and 1 yellow, or 3 green and 4 yellow. How many different sets of yellow and green rods can be chosen that will form a pole 62 centimeters long? All right, so basically 62 would equal green and yellow, right? So yellow is how much? 5 centimeters. And green is 3. So this is basically the equation. And what you're essentially just doing is you're trying to figure out integer solutions to this question. So I make a little table here, y and g, and off we go. When y is 1, you substitute this in, and you get g equal to 19. So that is one integer solution. When y is 2, you substitute this in, and you get 17.33. Well, that's no good because that's not an integer. And then you just keep going, right? 3, you would get 15.6 approximately, and then 4, you would get 14. So that is a integer solution. And then I can see that every 3, so I'll just jump to 7, and I get 9, and then I jump to 10, and I get 4. And then after this, I wouldn't get positive integers. You need positive integers, right? Because number of rods is always going to be a positive number. You can't have -1 rods. So how many integer solutions did I get? I got 4. So 4 is the answer. How many different sets? And you can list those sets. Part B, among the green, yellow, black, and red, find, with justification, 2 colors for which it is impossible to make a 62 centimeter length pole using only rods of those 2 colors. Okay. All right. So this will take a little bit more space. So let me just move this up. So this time we have green, yellow, black, and red. And those are the only ones. And our length was 3, 5, 7, and 9, according to that table up here. Okay. And they're saying that you want to make a rod with only 2 of these. So our combinations are either GY, GB, GR, or YB, YR, or BR. Those are the only combinations. And for each of these, let's see what the equation is. So for the first one, it would be 3G plus 5Y is equal to 62. And so on, right? 3G plus 7B is equal to 62. 3G plus 9R is equal to 62. 5Y plus 7B is equal to 62. 5Y plus 9R is equal to 62. 7B plus 9R is equal to 62. So those are the equations. And basically what they're saying is, which one of these equations are there no solutions to, no integer solutions? All right, well, let's see. This is just basically time consuming. That's all it is. Everybody knows how to add and subtract and all that stuff. So for the first one, I think this is the same as what we just did, right? Up here, it's 3G plus, yeah. So this one we already found 4 integer solutions. So I can just say we have 4 integer solutions. So as in part A, see part A. And then the next one, you guys can do this just like I did in part A. One integer solution, for example, is G equals 16, B equals 2. And then so on. You just kind of go from there. This is the one that has no integer solutions. This one, y can equal 11, b equals 1, that's one solution. This one, y can equal 7, r can equal 3, that's one solution. And this one, b could equal 5, and r could equal 3, I believe. So now you say, well, okay, that's great, but is there some quicker way? Well, you can look at that a little bit closer, like this one that has no solutions. What you can do is you can factor out a 3, right? And when you do, you get g plus 3r. And when you look at this, this means that this has to be divisible by 3. Or another way of looking at it, which may be better, is just to do the math. And G plus 3R, if you do 62 divided by 3, is 20.6 approximately. Well, G plus 3R can never be 20.6 because both G and R are integers. So if they're both integers, you can't get a non-integer solution with this equation. So that's one way of kind of analyzing it. And this is sort of the long way. All right, moving right along to the last question, part C. If at least 81 rods of each colors, green, pink, violet, and red, must be used, how many different sets of rods of these 4 colors can be chosen that will form a pole 2,007 centimeters in length? Explain how you got your answer. So we are told that we have to use at least 81. So what I'm going to do is first let's just get rid of that 81. So at least 81 of G, at least 81 of the P, at least 81 of the V, and at least 81 of the R. Now, we know the lengths that G, I believe, was 3 centimeters, P was 4 centimeters, violet was 8, and red was 9. So when I do this math, I get 1944. So that means 1944 is already accounted for. So that 2007 that they talk about, if I can bring it back in here, yeah, that 2007, 1944 of that is already been accounted for. So I'm going to subtract that to get 63, and the 63 is what I have to work with. You see what I mean? So that means that some combination of these 4 colors has to equal 63, and that's really the heart of the question. So this 81 business was kind of pointless, I think. I'm not sure why they even put that in there. Just to make you think a little bit, I think. All right, so this is what we have to work with now. So same thing, we have to get integer solutions. Now, unlike before where we had 2 variables, now we have 4 variables. So it's a little bit more complicated, but you can make your life a little easier. The first thing I notice is that we can factor this G plus 3R, and then you can factor out a 4 to get P plus 2V, and that equals 63. And what this does, I'll call this A and I'll call this B. It kind of makes it like a 2 variable problem. And there we go. Since it's a 2 variable problem, let's work with it like a 2 variable problem. So I've got A, B, and let's see what solutions I get. And of course, A and B are also going to be integers, positive integers, since they're a combination of positive integers, G and R or P and V. All right, so I'll let you do that. I mean, you guys can do this. Like, for example, if A is 1, what does B have to be for it to total 63, right? And it's 15. And then you kind of keep going, and you're just going to concentrate on the integer solutions. You're going to get a lot of non-integers, but eventually you'll see a pattern that this goes up by 4 every time, the value of A. So you can just concentrate on that. And I'll just fill them in, and I'll leave the math up to you because I'm sure you can do that. All right, so these are the integer solutions. Correct? All right, I said great, but that gives me A and B. I need values for G, P, V, and R. All right, well, that's what you have to do. For each of these guys, you got to, in a time-consuming way, come up with values for G, P, V, and R. So here we go. It's not too bad. I'll just do it quickly because I think you guys can do it on your own. But I'll just walk you through it. When A is 1 and B is 15, what do we get for G, P, V, and R? Okay, so if A is 1, that means that G plus 3R is equal to 1. And it means that P plus 2V is equal to 15. All right, so let's start with the first one here. This one right here. The only solution I can think of is GRPV. GRPV. I think I have to organize this a little bit differently here. Yeah. Those letters have to be organized a little bit differently because we're talking with G and R, and then P and V. Okay, there we go. Okay, so like I said, the only way I think it can work is with 1 and 0. But P and V, this one gives a lot more solutions, and then we kind of work with that. We can have, let's see, 0 and 15, 1 and 13, and then it kind of keeps on going. So I'll just fill them all in. 2, 3, 4, 5, 6, 7, and the corresponding values are 1, 3, 5, 7, 9, 11. Right. So I have one possible set there, and here I have, how many do I have? 8 possible sets, right? So 1 times 8 is the total number of combinations, which is 8. So you see how I did that? And that's what you have to do with each of these. So this one gave me 8 sets. Yeah. And they want to know how many different sets. So we got to do it for each of these. And I'll write it out. I mean, I don't think it's that painful for you guys to do. So I'll just do them here. So I'm going to need 5 slots, right? Okay, so here we go. And I'll do it quickly because I'm sure you can do it on your own. I just want to write it all out for you. Okay, so what's the next one? Next one is when A and B are 5 and 12, right? So that means G plus 3R is 5, and P plus 2V is 12. So similarly, if we have G, R, P, and V, we are going to get the following solutions. 5 and 12 this time, right? Okay, so for this guy, the only solutions are 5, 0, and 2 and 1. For P and V, we have a whole bunch. 0, 1, 2, 3, 4, 5, 6, and the corresponding values for P will be 12, 10, 8, 6, 4, 2, and 0. So we have 2 here, and we have 7 here, so 2 times 7 is 14. So 14 goes here. So hopefully you get the hang of it. It's just time consuming, that's all it is. I mean, the mathematics is easy. It's just, multiplication and subtraction and all that, but it's just time consuming. So 9, 9. So same story, G plus 3R is either 9, and P plus 2V is either 9 again. So GRPV, let's see what combinations we get here. Let's see here. I think it's just 0, 1, 2, 3, and then 9, 6, 3, 0. And then for the PV, it's 0, 1, 2, 3, 4, 9, 7, 5, 3, and 1. Yeah. So we got 4 here, we have 5 here, so we have 4 times 5 combinations here, which is 20. So this is 20. All right, let's keep going. A, B this time is 13 and 6. Same story. G plus 3R is 13, and P plus 2V is 6. So G, R, P, V. Let's see what we get for this combination, 13 and 6. I think we have 0, 1, 2, 3, 4. And then we have 13, 10, 7, 4, and 1. And then here we have 0, 1, 2, 3. We have 6, 4, 2, 0. So we have 5. Here we have 4. So 5 times 4 is 20. So that's 20. 2 more to go. And this is A and B. Now we have 17 and 3. G plus 3R is 17. And P plus 2V is 3. So this time G, R, P, V. Let's see what we get here. I think 17 and 3 would be 0, 1, 2, 3, 4, 5, and then 17, 14, 11, 8, 5, and 2. And then for PV, for 3, I think the only ones are 0, 1, 3, 1. So this is what? 6, and this is 2. So 6 times 2 is 12. All right, and we are almost done. One more. We have A and B now at 21 and 0. So G plus 3R is 21. And P plus 2V this time is 0. So let's see. For G, R, P, V, let's see what we get. For 21 and 0. For R, oh boy, a lot of combinations here. 0, 1, 2, 3, 4, 5, 6, 7. And then this will be 21, 18, 15, 12, 9, 6, 3, and 0. And then for P and V, the only combination is 0, 0, interestingly. So this is 8, and this is 1. So 8 times 1 is 8, and there we go. And now we just have to add up these guys to figure out the total. So let's see, 20, 40, 60, 74, plus 8 is 82. So as you can see, time consuming, but the math is actually not so bad.